Okay. So that's super janky, but whatever. Okay. So can you guys remotely hear me? And that's a decent.
I can hear you. There's times where it lags, but I can still hear you fine.
All right. Well, this will work for today then. You guys are on my laptop, which is why it's worse. Okay. So let's see. So first, let me take attendance. I'm going to lift you guys up remotely to take attendance here. Okay, so that's y'all. Okay, and then the present people. Jojo. Here. Okay. Can you put your mask up, please? Christoph. Benjamin. Okay, sorry. Hope. Noah. Anna. Nicholas. AJ. Here. Kaylee. Alexander. Here. All right, cool. So, let me make this a little bit. So what we're going to be talking about today is talking more about limits. And today we'll be focusing a lot on just understanding what they are, using some tables and graphs, but as a reminder, down the road we'll want to break away from that and to figure out how to do it without those tools. So as a reminder, the limit as x goes to a of f of x equals L. So what this means, so f is some function, a is kind of an input, an x value, and L we're thinking of as a height. And so what this means that for really inputs x, getting closer to a, if we look at the corresponding outputs f of x, they get closer to this number L. So the idea is really, we made a table last time, and the idea is if we, on the first column, take inputs that get closer and closer to whatever number we picked here, we put those into the function f we're looking at and generate a new column of outputs. Then the list, that column of outputs, will get closer to whatever number L this is. And so the way that these problems will really be presented is we're going to be given some function f and some point a and figure out what is the limit of that function at this particular point a. a few things before we get going, and I'll do this in red as kind of a warning. So note that if you just write this on its own, so the limit as x goes to a, without a function, doesn't mean anything. Yes.
Okay, let's say you have limit x goes to a, but then you have an output which equals out. Does that still mean anything?
So if you wrote,
function?
so what I mean is, if you wrote something like this,
Oh, you need f of x.
yeah, so this is some number you're looking for. This is like saying equals 5. Like it doesn't mean anything. You don't know how to understand it yet. So you really do need the function there. And this is a little tiny bit better, but something like the limit of f of x is kind of sloppy. So if here what's missing is you don't specify which point you're moving towards. You're not saying the limit at whatever a you're talking about. And that's the kind of thing where you might say, I don't want to write the whole thing 20 times in this problem. Well, 20 would be a lot, but 5. And so try to also stay away from this. Also, before we get into what we're looking at, we aren't following the textbook super closely. I mean, not like going through the material in exactly the same order. If you look in the textbook, chapter 1.2 has a very different definition of limits, or it's different in that it's more precise and looks at it in kind of a different way. We're not going to be messing with 1.2. So if you happen to look through that and it looks really foreign, it should, and you don't have to worry about it. So let's ask the kind of question that we'll be asking. So what is the limit as x goes to 2 of x squared plus 1? This is a sort of typical limit type problem. You're given a function and a point. What number is this? So it's saying, what number do you get if you let x's get closer and closer to 2, put those x's in here, x squared plus 1, and then generate a list of outputs. So to start figuring out and getting used to limits, we'll start by just making a table. So what this means is we'll pick some x's, that keep getting closer to this number 2. So these are things like 1.5, 1.9, 1.99, and to be extra careful, 1.999. And what we're going to do is these will be our inputs. Then we'll do some calculator work. Well, I did the calculator work. You'll take these x's, square them and add 1, and see what numbers you get. And if you do this, and this isn't exciting, it's just calculator stuff. If you put in 1.5, square it and add 1, you get 3.25. You put in 1.9, 4.61, 1.99, 4.9601, and the last one, 0.999, you get 4.996001. And you could keep going, but in this case, it feels pretty, or hopefully it seems clear what's happening. What number is this list getting close to? 5. 4.99, and especially these last two, they make you think, if I keep adding 9s, I'm going to get more 9s, and then maybe a 6 and a bunch of zeros and a 1. So what this suggests is that the limit as x goes to 2 of x squared plus 1 equals 5. And so this is that limit we were looking for. The number 5 is the number these outputs get close to as the inputs get close to 2. What we can notice here, and which is maybe makes you think that this limit stuff is not really a new thing, is that for this function, x squared plus 1, f of 2 does actually equal 5. So here, this, if you look at this, you might say, well, this answer 5 makes sense. Since at 2, my function is actually 5. If I'm close to 2, my function should be close to 5. And that is what's happening. And we especially can see this if we look at the graph of this function. So graphically, so x squared plus 1, it's a parabola that's been shifted up 1. That's what that plus 1 does. So it looks something like this, right there. And so what this table is really telling us is if we picked these x's as inputs, so that would be saying pick x's over here, getting closer and closer to 2. If you take those x's and put them into the function, you get the height of the points on the graph. So you would get some points on the graph that are moving up. And what we're noticing is as our points get closer and closer to 2, let me actually label that. As our points get closer to 2, the corresponding heights are moving up and getting closer and closer to this height of 5, which matches all the numbers that we saw over here. What we could also have done but didn't do is, if we're looking at points close to x, that could also be things like 2.1, things that are a little bigger than 2, but not right at 2. And I won't make the table for that. If you do that, trying things like 2.1, 2.01, you'll see that the list you generate gets closer and closer to 5. Graphically, how that looks on our graph here would be, if we pick some x's over here, a little bigger than 2, we get some points on our graph that are on the right side of our point, that are further up the parabola. So they're right here. And now, as we're moving closer to 2, we're going this way. The corresponding points are moving down. And again, as our x's get closer to 2, these heights get closer and closer to 5. Questions about this? So if this seems like there's not a lot going on, good, because this is the case where things are nice. What a lot of this limit part of the course is, how does this idea look when things aren't quite as nice? And here's an example of that, which is actually really close to this, but different in a particular way. So let me define a piecewise function. G of x, one of these is a good one. So what this function is going to look like is it's going to be x squared plus 1. So the same function that we had before, everywhere except 2. And then we'll say that at x equals 2, it's going to be 1. So what this looks like is really close to that other graph that we had there. So let's see, 1, 2, 1, 2. So what it looks like is basically everywhere, it's the same parabola that we had before. But at this point, x equals 2, it's not up where by the rest of the parabola, it's down here at 1. So then we can ask a question about this function. So what is the limit as x goes to 2 of this parabola with a hole in it? 1. So that is, well, so that's, what makes this weird is that that's not actually correct. But that is kind of the first guess. Well, you'd say, well, the function is here, and this is asking what's happening to the function at 2. But it's not exactly asking that. Because mirroring this picture, what we're saying is, pick x is close to 2, look at the corresponding points on the graph, and what happens to those, and as you let those x's get closer, what's happening to those heights? And so what is happening to those heights?
They're getting closer to 5.
They're getting closer to 5.
This is that anomaly.
Right, so here, and the same thing happens on the other side. If you're getting closer to 2 from the other side, you're going down. And again, getting closer to 5. And actually, what happens is if you wanted to make a table for this, it would be exactly this table. Because when you're making this table, you're never actually using the x2. You're always using other x's, which on our graph means you're always using this parabola. So this is the kind of thing that can happen. And when you're talking about limits, the question is always, what happens as you get close to a point, but you don't ask what's happening at the point? That's just a different question. And so this is a kind of weird problem. But that's one way in which these limit questions really are different than some of the problems you've seen before. Yes?
So could the limit not be 1 for this problem then?
So here,
No matter how you look at it?
right, so in this case, oh, I should answer that, sorry. This limit is 5. Even though, and here's the way that things are different, g of 2, this is what is the function output at 2, And that's where this point comes in. So G of 2 is 1. If you actually input 2, you actually output 1, but inputs really close to 2 give you inputs close to 5. And so that's where these evaluating at a point versus finding the limit are different, or they can be different. What we saw in this case, without the hole, they matched up. So that's one thing we'd like to know. When do they match up? Because this was pretty easy. What you might suspect, and you're pretty much right, piecewise functions give us a lot of weird, different limit behavior. So some other examples, which I'll pull the graph up in a second, and but on the board I'll just put some tables. So let's look at this function. Let's look at these limits. A is the limit as x goes to 0 of sine x over x. And B is the limit as x goes to 1 of sine x over x. And these two actually are they have different things going on, which suggests, at least to, if you're looking for it, that questions about limits, there can be some strange things going on, and it takes some real effort to understand. So for A, one thing that we can notice first, which says that, well, I'll save that for later. Let's make a table for this. This is one where you really are going to need a calculator, because all of these decimals in sine just becomes a mess. So if we're looking at x is close to 0, we can say things like 0.1, 0.01, 0.001, and what happens as we put those into sine x over x. And I did this calculator work. You can check it or go further down the list if you want. But the list we get is 0.9983341. For you guys watching from home, to make sure you get these numbers, you might want to check the lecture notes that I posted. Also, you guys, for the remote viewers, all these lecture notes are posted, so you have what I'm writing down if you're worried you didn't copy it correctly. Okay. For 0.01, it's a bunch of decimals too, 0.9999833. If we put in 0.01 into sine x over x, 0.9999998. So what does it look like the limit is? 1. So here, again, and this is a strange thing about limits, and this is correct, so I'll write it down. The limit as x goes to 0 of sine x over x is 1. So this 1 never actually appears in this table. It's what does this list look like it's getting close to? And these longer and longer strings of 9s say it looks like this keeps getting closer and closer to 1. A few things to point out about this is that You could also have done this by using x's close to 0, but on the other side. So there, you could also have made a table with -0.1, -0.01, -0.001. Those are also numbers getting closer and closer to x, just they have to be negative and they're moving up towards it, rather than positive numbers getting smaller and smaller. And if you make a table, you'll see the outputs also are closer and closer to 1. And a second thing to notice about, or to point out about this, is that sine of x over x is undefined at x equals 0. So you can't put 0 into this. This, its domain doesn't include 0, but its limit does exist at 0 and actually heads towards 1, which is a kind of new thing. It's not even defined there, but its limit still exists. It is equal to 1. Yes.
I missed, how did you get the y figures?
These ones?
Yeah.
So here it's putting these x's into this expression, sine of x over x. So this one is sine of 0.1 divided by 0.1. And that's a gross decimal, and they cut it off at 7 decimals because that's already more than we probably needed. So let's look at this other one. Here, again, if we make a table for this, we pick some x's getting closer and closer to 1, and we see what happens to the list that we get. So x is getting closer to 1, things like 0.9, 0.99, 0.999. And in this case, I actually will write out the other side. So we could also say things like 1.1, 1.01, 1.001. These are numbers getting closer and closer to 1, but they're getting smaller, rather than the 0.9s keep getting a little bit bigger and closer to 1. And if we make a table here, this is where we see the table way of finding limits isn't really the best. So here's what you get if you put these x's into this function. 0.9 gives you 0.870363, or at least rounds to this. 0.99 gives you 0.844471. The 3 nines, 0.999 gives you 0.841772. And if I asked you, what is this getting close to? It's not clear. This seemed like some more and more 9s, that's getting close to 1. This is just a bunch of decimals. It's kind of leveled off here with 0.84, but there doesn't seem to be a pattern. So if we try the other side, that'll give us some more information about what this thing is getting close to. So working our way up this time, if we put in 1.1, 0.810189, 0.01 there is 0.838447, and 1.001 is 0.841170. I apologize for all these decimals. We will stop having examples with huge decimals. But just as we're beginning to figure out what is going on. So here we're seeing, okay, there's this 0.841 part, so maybe that's leveled off, but it's still just these decimals here. So we don't really know, but it turns out that the answer is not as complicated as this just bunch of decimals makes it seem. So actually, this limit, the limit is x goes to 1 of sine x over x. This equals sine of 1, which, a little suggestively written, is sine of 1 over 1. And as a decimal, if you put sine of 1 in your calculator, this is 0.841470985. So on one hand, this is not something we would have guessed from the table. It's a bunch of decimals, and you probably wouldn't have gotten that. But on the other hand, what happened is this is the case where finding limits was actually the easy situation, because this number is what happens if you put the 0.1 into this function that we're taking the limit of. So this is actually the kind where finding this limit, we could have done it by just saying, put 1 in here, you get a number out, that's what it's getting close to. If you're close to 1, the output is close to what you get if you actually put in 1. So first I'll pull up a graph of this, and then I'll write out some questions that are suggested by these two. And before I pull up the graphs, are there questions about what all of these decimals mean? As that warms up, let me write out a couple of these questions. Which aren't like problems to do, but questions about how do we move forward in trying to learn about limits. So one question is, when can we find limits by evaluating? Meaning, in this case, if we had known just put in 1, see what number you get, and you're done, that would have been much better than making this whole table. And after the table, we still didn't have a good idea of what the number was. So that's one question, that if we can identify when we just evaluate to find limits, that makes everything a lot easier, because evaluating functions is something you've been doing for a while. So let me pull this down. So if we look at this function that we have, sine of x over x. So this is not a graph that you've likely seen before. That's a little better than that. That's too dark. So this is not a graph I would at all expect you to just know. So given the kind of problem of the limit, it's like, well, this isn't something that you would do without a graphing calculator. But what we can see from this is that the limits we computed from the tables are what match up. At 1 here, the function is nice and one piece, and as you get close to 1 from either side, so here, if you watch that y coordinate, the values keep moving up towards that 0.841 that we saw. And if we move from the other side, the values keep heading down towards that 0.841. And at 1, I can get on it. Exactly. We get that 0.841. So here, because it's nice and smooth the whole time, as you get close to 1, you get close to the value that it actually takes at 1. At 0, what we see is if we try to get at 0, at 0 it's undefined, which we can tell from the equation there. You can't divide by 0, so you can't put 0 into this. But also, the limit exists. As you get closer, this number gets more and more 9s. As you get closer from the other side, you get more and more 9s. And so we see what we did from the table. So from the graph, even though it's not defined at 0, it is heading up both sides, leveling off towards this value 1. That second, or that point at 0, there's a question there that we should ask. How do we find limits when, I'll put this in sarcastic quotes, evaluating gives you 0 over 0. So if you take this function sine x over x, if you try to put 0 into it, both the top and bottom become 0. So there you really can't find it by evaluating, just because you don't get anything at all when you try to put in 0. But despite that evaluating this at 0 makes no sense, it still has a limit there. Kind of a meta question above all these is, how do we answer these without appealing to a table or graph? But a big question also is, what else can happen with limits? Because the things we've seen is a couple examples. Finding limits is just the value at the point. In this case, the function isn't defined, but the limit still exists. This limit is still a number 1. In this case here, the function is defined, but the value of the function is different from the limit, because we have this hole and our point is put somewhere else. So we might ask, these are a couple of weird things that can happen. What else can happen? And let me put up a graph that shows us another weird thing that can happen when we're talking about limits. And as in this case, it happens with a piecewise function. So let's look at this piecewise function, which is 3 if x is less than or equal to 0, and it's going to be x squared if x is greater than 0. So what does the graph of this look like? Well, on the left half, when a function is constant 3, that means it's a horizontal line up at height 3. And so we're using a horizontal line up at 3, starting at 0 and then going left. So the left half of our function looks like this, just a flat line at height 3. For the other part, we're using x squared, the standard parabola, starting at 0, but not including 0. So at 0, we'll put this little circle just to say, don't use the parabola here, the function is up on the line, but then we have the parabola that we're using for the right half. And then the question, well, if we're talking about limits, there's really a kind of obvious point where we should ask what the heck is going on, and that's what is the limit as x goes to 0 of h of x. This point where we switch from one piece to the other piece, what do we want to say about that limit? And what value do you think this should be? 3. So there, where that comes from is you say, well, limits, say we're looking at 0, so let's pick some x's getting close to 0. Look at the corresponding points on the graph. And here it's a little weird because what you might say, well, normally limits are you get closer and closer, but here it's just at 3. So it's already as close as you can get and it's not going anywhere. So here, and to write this down, for x below 0, if x gets closer and closer to 0, h of x gets closer to 3. And really, it's already there. It's the kind of silly case where it doesn't have to get closer and closer, it just has to not leave. But the answer isn't 3. What else might you say it is? 0. So there, a way that you can get 0 is saying, well, limits, like we did in this example, you have to check both sides. If we look at x's over here and let those get closer to 0, that gives us points on the parabola. And those points, as we move down the parabola, head toward this height of 0. So for x bigger than 0, if you let them get closer and closer to 0, then the function, which is on the parabola over there, gets closer and closer to 0. And then we have to decide what to do. Yes. Right. So the resolution for this situation is the limit is a number. A meaning singular. The limit is the number the function gets close to as you let the inputs, in this case, get close to 0. And if you're in a situation where there are 2 options, what we'll say is that here, the limit doesn't exist. Abbreviated, you want DNA. So it's that climax of Mean Girls, the limit doesn't exist. Just watch that movie. That reference keeps getting more dated. But the resolution is the limit's a number, and if there's more than one option, we'll say the limit doesn't exist. And so that's a possibility. When you write this down, it's possible that there isn't a number that works. And if there isn't a number that works, then just say this thing you wrote down doesn't exist. It doesn't refer to any number.
And that's just the limits.
Right. So if you go back through all the examples that we've seen, if you check both sides, if they both went to the same number. And while I didn't always do it, I did say you sometimes need to think about both sides, and this says you really do need to worry about that. But, okay, so the limit doesn't exist, but if I said, just look at the right side, it looks like the function's going down to 0, which is basically what this line said. And if I said, just look at the left side, it looks like it's at 3, and that's what we saw here. So we can still make sense of these ideas. We just have to specify, just look at one side or the other. So here, we get a well-named definition, which is one-sided limits, which I'll write it out carefully, but it's basically just look at one of the two sides. So the notation is the limit as x goes to a with a little negative above it of f of x equals L. And this is said to be the limit from the left of f of x at a equals L, or the limit of f of x as x approaches a from the left. Also sometimes called the left-hand limit at a of f of x is L. So from the left, and this negative is supposed to tell you on the number line, negative direction is to the left. What this is saying is that for x less than a, if x gets closer to a, f of x gets closer to L. So it's still the same idea. You're making a table or looking at the graph, but what you're restricting yourself to is just look to the left of A. And just to finish up, since we're basically out of time, you can also look from the right side. That has a similar looking notation. The limit as x goes to a with a little plus of f of x equals L is the right-hand limit, or limit from the right and this is the same thing. It uses x greater than a. So to put these two into what the example we've looked at, and this is where we'll wrap up for the day. So if we write this down, the limit as x goes to 0 from the right of h of x, this is saying, here's our function, go to the right side of 0, which means we're on the parabola here. And as we saw here, if you're on the right side and let x get close to 0, you're moving down the parabola, and so the heights also get close to 0. So this really corresponds to this right there. And we also figured out the other side. The limit as x goes to 0 from the left of h of x. You're on the left side. For these x's, the function is the line, and the line is staying at 3 the whole time. So that corresponds. So where we'll pick up, and on Monday, the people here are going to be watching from home. You guys at home are going to be here, and we'll keep talking about limits, some one-sided limits, but also some more things that can happen. Okay. Have a good first weekend. Celebrate the end of your first week responsibly, and I'll see you guys on Monday.
I got my schedule and everything.
Okay.
But I think I messaged it on Roll Attendance.
Okay, yeah, okay. So I think, all right, so I think what I'm gonna do, actually, I'm gonna, as a few people are getting things figured out, I'm gonna post the videos from those and I'll have like YouTube links on Canvas. So you can take a look at those. We just did some of the pre-calculus review.
Okay.
So you didn't miss a quiz or anything. Yeah, so take a look at those videos and look over the solutions that I posted. And kind of
I can
look
do
for,
that
yeah.
this week. Thank you. Oh, my bad. I didn't know.
Oh, my lab. So is it on?
Yes.
Okay, I don't have pictures for that.
So on, what's this?